Now let us move to the program part. The upper half section we are using, since it's the pull-up transistor, we are using just a syntax, the keyword called as pull-up, within the parenthesis net B. And for lower transistors, we are going to use 3 NMOS transistors. We have to instantiate the ideal MOS switch NMOS. Within the parenthesis, we can represent the inputs and outputs. Here supply 0, a net A is connected to supply 0. Output is B here. And supply 1 is not represented. We are not using supply 1 directly, since we are going to use it as pull-up of B. No need of using any supply 1 also. That statement supply 1 here. Coming to the program, module name. Module name is user defined. Within the parenthesis, we have to represent the inputs and outputs. The inputs for the lower transistors are in1, in2 and in3, and the upper transistor gate is shorted to source. So VGS equals to 0. No, we are not using any input there. And output is B. We are specifying the output as B here, and the inputs as in1, in2, in3. Net A is connected to supply 0. The intermediate signal called as B, which is nothing but the output, we are declaring it as the Y declaration. Then 3 lower transistors, enhancement MOSFET transistors are used. We are instantiating the ideal MOS switch as NMOS. We can instantiate the NMOS for three times, or else we can instantiate the MOSFET for only one time, and we can give the inputs and outputs for the corresponding transistors separated by the comma. So we can write in either way, either instantiating for 3 times or instantiating for only one time, and then separating the 3 transistors input and output combinations with comma. So when we are going to see the circuit, here the output B and the supply 0, which is acting as one of the input here, is connected to net A. These are common for all the 3 transistors, and they are defined only by the inputs that we are going to give at the gate, that is in1, in2 and in3. So we are instantiating the NMOS here, then output B followed by inputs. Actual input is A here, and the control input is in1. This is defining for one of the transistor. In the same way, we are defining the inputs and outputs for another NMOS transistor with the help by separating it with the comma. So output is B, input is A, and the control input for the second transistor is in2, and the control input for the third transistor is in3. As this statement, we have defined all the 3 transistors using a single instantiation, and then we are terminating with a semicolon. So upper transistor is nothing but the depletion MOSFET NMOS transistor. Simply, instead of instantiating that particular transistor, we are using the pull-up keyword within the parenthesis. Net B is connected to VCC, nothing but supply 1. So we are just specifying the particular keyword as pull up. Within the parenthesis, the net is B. B is connected to supply 1. Then starting with the module, we are going to end this particular module. Coming to, this is the main design module program, and the lower half section indicates the test bench program for the main module program. So module name of the test bench is again user defined. We can use the braces without specifying any inputs and outputs. Inputs are represented in the form of registers in the test bench, and output is represented in the form of the while declarations. We are instantiating. What for we are writing the test bench program is to test the main design model program. So we are instantiating the main model program by its name here. And NN is the present name of the test bench here. Whatever may be the inputs and outputs that we have specified, the same order we have to use in the test bench also. Means in1 in the test bench is port mapped with in1 in the design module, in2 is port mapped with in2, in3 is port mapped with in3, and B is port mapped with B. So we are connecting the test bench program inputs and outputs with respect to the inputs and outputs of the design program. We have to use the same order here. Then we are giving the set of inputs using either the initial block or always block. Difference between initial and always block is within the initial block, the number of statements are going to be executed for only one time. Whereas always block, depending upon the condition, it executes number of times. So here, using initial block at 0 time instant, as no time instant is mentioned before this particular statement, the time instant here we can take it as 0 nanoseconds. At 0 nanoseconds, in1, in2, in3, all the 3 inputs are assigned to logic 1. Then end. We are using the always statement. 3 always statements are used. All the always statements, if you are going to use more than one always statement, all the always statements run concurrently. Run concurrently means parallelly. So always has to means for every 2 nanoseconds, the in1 is going to be complemented. As already said, the always blocks run parallelly means for every 3 nanoseconds, in2 is going to be complemented, and for every 5 nanoseconds, in3 is going to be complemented. Then to display the results, we are going to use either $monitor or $display statement using the initial block. So here we are going to use the $monitor. Whenever the input variables are going to change their values, for all the time instances, the output is going to be displayed. So first, it specifies $time, specifies the time at what instant the inputs are going to be given and output is produced. So input is represented in the form of binary. Percentage B stands for the binary. Input 2 is also represented in the form of binary. Input 3 is also represented in the form of binary. Output is represented in the form of binary. And what order this must be displayed is shown here. First in1 will be displayed, then in2, then in3, and at last B is going to be displayed. So when to stop this particular execution of this particular program, we can use two statements. Either we can use the $stop or we can use the $finish. $finish means the particular execution comes, the process of simulation comes out of the execution process. $stop means the particular process is going to be suspended for certain amount of time. So here we are using the $stop, and at 24 nanoseconds, the execution process is going to be suspended for certain amount of time using this particular statement. So started with the module, we are going to end this particular module.